Good morning, everybody. Welcome to another wonderful morning on Chem 1105 with your host, me, Dr. White. I don't know about you, but good morning, Ruben. I had a busy weekend. I went to war with my backyard. I spent about 2 hours Saturday and Sunday morning trimming bushes, knocking down heavy weeds. I still got about an hour and a half more this coming weekend. Next Monday is brush pickup where I live. So just put it out front and they take it away. And I have a lot. All right. Important announcement. Don't forget, Friday will be test number 1. Hopefully you've done the practice problems. Hint, big hint, and do them. They'll help you for test number 1. Test number 1 information is already on Blackboard, and you should have gotten an email. I talked about it last week. And also this Wednesday, I'll do my world famous review for the next test. In this case, it's test number 1. I like those special effects. But it's obnoxious Monday. Look out. All right. Also, don't forget, keep on handing in the labs. Lab is due tomorrow. I've already posted the lab we'll be doing tomorrow. If this morning I posted your lab, I think it's lab 2 scores. Don't forget, there's no such thing as a dumb question in my class. If you ever want to know how you did on a lab or why I took off points, ask me. That's what I'm here for. All right, let's get started. All right, last week, Friday, seems like a long time ago. It must have been all that work I was doing in my backyard. Luckily, I work out with weights, so I have no muscle strains, hurts, or anything, which is a good thing. All right, talking about switches off, click. This won't be on a test, but VSPER, which stands for valence electron pair repulsion theory. Molecules are not flat. When you write water, and if I were to do the Lewis structure, you say, oh, that's flat. The answer is no. Molecules have shapes. And the Vesper theory is used to determine the shapes of molecules. And hopefully you all can see from Wikipedia. Thumbs up, people. Do you see it on your screen, some stuff? And these are the different shapes molecules have. And it's dependent on how many bonds, chemical bonds, and non-bonding electrons to a center atom. And that tells the shape that atom of a molecule will have. Now, in water, you have 2E means no bond or non-bonding electrons, and X would be hydrogens, and O would be oxygen. And water is bent. And you see different ones. And here they show you an example of bent molecules like water here and different things. Now, important thing I'll talk about later is when you have tetrahedral. Notice you have the red in the center, that's a carbon atom. Each circle or ball at the end would be hydrogen, CH4, and that's your natural gas. And if I click on this, they show you methane. Let's see, I guess the picture's up in front right here. And here you can see the picture of the molecule. So depending on how many bonded and non-bonding electrons an atom has, it will determine the shape of the molecule. Now, you're probably looking at this and say, why am I learning this? Well, guess what? It affects your RNA and DNA. The shape of that is determined by Vesper theory. Now, I have here a model, which you saw earlier. We use these in organic chemistry. And the center carbon, each one is a bond. If there are hydrogen here, methane, your natural gas. And notice it's got what's called tetrahedral. Each side is a tetrahedron, and the bond angles are specified. And this plays an important role of things like your skin, my hair, what's left of it, my beard going almost totally gray, and a whole lot of other things in our life. So why are you learning this? Because it's in your daily life. And like I said, molecular geometry shape based on the number switches off of electron pairs of an atom. And here I showed you water, methane, CH4, ammonia. It's called trigonal trigonal pyramidal. And there's non-bonding and bonding electrons. Now, switch is still off, but this is a concept we're going to come back later on. Let me turn it on partially, whatever that means. All right, let's talk about electronegativity. Bet you didn't learn? No, you were going to learn a lot of neat words in my class. You will. That's the ability of an atom to attract electrons to itself. Think of electronegativity as how strong an atom is of an element to keep the electrons that are in a chemical bond closer to itself. Now, this is important. Electronegativity of an element increases as you move from left to right in the periodic table and as you move from bottom to top of the periodic table. So I better get a periodic table open. And hopefully everybody sees a periodic table on your screen. When you go from left to right, you have more electronegative. And when you go from bottom to top, it's one of the most electronegative items, and this doesn't really include the noble gases, is fluorine. Oxygen is very electronegative. So is nitrogen. Carbon is so-so. Hydrogen, and lithium, sodium, and potassium, they're pretty weak, especially hydrogen. And what does that mean? You have a whole bunch of different types of bonding, which is totally off right now. Nonpolar is when you have a chemical covalent bond between atoms with identical or very similar electronegativities. It's truly equal sharing of pairs of electrons. Now, polar covalent, and again, switches off right now, it won't be on a test, is a covalent bond with different atoms with different electronegativities. And what we mean by that is we form what's called dipole. In organic chemistry and chemistry in general, di means two. Di means two. And pole is for polarity or charges. And a dipole is a polar bond that has separate positive and negative charges. This charge separation is only partial. It's not a full charge separation like an ionic bond, since there's still some sharing. And we indicate this by using the lowercase delta the Greek letter, lowercase, delta capital means difference, lower delta means small difference. And example of this, and now I'm going to get something very important. Let's talk about water. In reality, and I'll use the line for two electrons covalent bond, because organic chemists do that. If you want to do that in a Lewis structure, I'll let you. Now, hydrogen is weak, small electronegativity, but oxygen is strong or high electronegativity. So in water, there's a slight positive charge on the hydrogens and a slight negative charge on the oxygen. Now, you might say, well, what's this? So what? Which is a good question. Let me draw the molecule. Two of them, water. And again, each, I won't put the non-bonding electrons in. I'm showing the partial charges on water. Now, if you have two water molecules, A and B, one from column A and one from column, I told you it's obnoxious Monday. It's getting there good. What you have is a very slight attractive force between two water molecules, the oxygen on one and a hydrogen on another. And if I were to draw another water molecule, this would continue on. And for this, I'm turning the switch way on. Whenever I put 3 stars and then IMP, that's a P, and an exclamation point, my notes, that always warned me, you better really know this. And here it is. Now, what is this called? There's a name for this attraction right here. It's not a real chemical bond, but still they call it hydrogen bonding. And this is something you should know. Now, what's the ramification? Ooh, expensive word there, of hydrogen bonding. Because the molecules of water are held slightly together by this tiny little force, it's not a true chemical bond, but still important. Water, like I have my bottle here, is a liquid. Now, if you look at similar molecules of similar molecular weight, they should have similar boiling point. That's the temperature which a liquid becomes a gas. Now, all the other molecules that have the same molecular weight, how much it weighs, of water are gases right now at room temperature. But look at water. It's a liquid. Why is this a liquid whenever it should be a gas? Hydrogen bonding. Hydrogen bonding makes water an exception. It makes water a liquid at room temperature. And because of that, that affected how life evolved on our planet. If we had gas as water, you wouldn't have your blood like this as a liquid, because blood is mainly water. You wouldn't have the oceans we have today. A whole lot of other things about hydrogen bonding. Oh, by the way, hydrogen bonding plays an important role of the shape of your DNA, which is important in life. I should warn you, Last time I took biology was freshman year of high school. Not that there's anything wrong with biology, but by the time I was even in 8th grade, I already knew I was going to be a chemist, and I became one. But my tea, which is water, is a liquid that I can drink because of hydrogen bonding. And it's truly important force in our world today, even though it's just a tiny little thing. Now, one way, don't tell my older sister I'm telling you this story. I have 2 sisters. I'm in the middle. I have one 7 years older, one 7 years younger. And the younger one was spoiled rotten, but all younger ones are, I guess. If you're a younger one, I apologize. But one time we were out in a rainstorm coming home, walking home, we had only one umbrella. And my older sister at that time was way older and bigger than me. I think I was only about 5. She was 12, so she was bigger. And we shared the umbrella, but because of electronegativity, she was stronger than me. She shared it more over her than me. I didn't get too wet if I had had no umbrella, but it was a lesson in electronegativity I learned at a young age. I got back at her later on in life. All right. And because of that, you can have polar molecules where the dipoles cancel out. In water, there's no true charge, but still the charge on hydrogen and oxygen are important. Ammonia is another compound that can hydrogen bond, but not like water. Oh no. Remember, this chapter is on test 2, not test 3. If you look, we're at the end of a chapter. And you know what time it is? It's new chapter time. New chapter time. What's this new chapter going to be? By the way, if you look in the syllabus, I was thinking of putting chapter 11. I'm going to put that at the end of the semester. I think it will work better. And that new chapter is chapter 5. The book calls it chemical accounting, but let's get into it. Switch is on. Now, when we talk about chemistry, the fun part is a chemical change, or as we sometimes call a chemical reaction. Then I'll never ask you what's a chemical change, but I'll talk about it. So you should know that's when an original substance is converted to a new substance that has different composition and new chemical and physical properties. And what would be an example of that? Well, if I took hydrogen gas and reacted with oxygen gas, and you need a little spark, you'll make water. And water has different chemical properties than oxygen and hydrogen, and that's a chemical change. When you eat food, hopefully you chew it before you swallow or you'll choke. When I was about 2 years old, I didn't believe my mother about that, and I found out she wasn't lying to me. Oh, by the way, I did live, in case you were wondering. And when you chew your food and swallow it, it goes in your stomach and it undergoes a chemical change, converted into different things. Now, the original substance in a chemical change, we call this a chemical reaction. That's the original substance changes to new substances with different physical, I could have also put down here chemical properties. Now, how do you know, and especially inorganic, which was mainly what we're going to do this semester, how do you know you've had a chemical reaction? Well, there are 4 things that are evidence for a chemical reaction. One is a color change. If you have something that's yellow and it goes blue or red or green or black when you mix two things together, that tells you you've had a chemical reaction, a color change. Now, I'm not talking about just turning a lighter blue or red, it changes actual colors. Now, another way to talk about a chemical change or know when a chemical change occurs is when you see formation of gas, otherwise known as bubbles. And again, formation of a gas proves you've had a chemical reaction. Now, another way, the third way, is when you see a formation of a solid. Organic chemists or chemists in general call this a precipitate. How many of you, I don't own one, but my sisters did. Do you ever see the snow globe, the paperweight globe with the snowman in there? And you shake it up, and all of a sudden the snow starts falling down. Hold on, let me try something real quick. Maybe not that quick. I'm trying to find one and I can't. Oh, that's disappointing. Anyways, I'll pretend I got the globe. You shake it up and you see the particles of snow falling down. Organic or chemists would call that a precipitate. If you mix two things together and you see a solid form, guess what? You've got a chemical reaction. Now, one place where a solid forms you don't want to see is when you get rust on your car. Luckily, I wax my car religiously, and I've got one. It's more than 10 years old. I just got a tiny little speck of rust on there. But when the metal changes to rust, guess what? It's a chemical reaction. And finally, the last thing that's evident of a chemical change is when you have a change in temperature when you mix two things together. If you take two things, mix them together, and it gets cold or gets very hot, you have a chemical change. How many of you have ever seen those packs you can buy that if you sprain your wrist or ankle or you need a cold pack, you take it, break it, shake it up, and you feel it, it gets very cold. And there you're mixing two things together. What you're breaking is a capsule inside that has one chemical and the other chemical is water usually. And you shake it up and that helps things mix, which I'll teach you about later. And it gets cold because a chemical reaction is occurring. Now, good news, tomorrow we'll be doing in our lab, a chemical lab that you will be looking for when you mix two things together, do you get a chemical reaction? And I'll talk about this again tomorrow. When you see a color change, chemical reaction, formation of gas, meaning bubbles, chemical reaction, and formation of a solid, that means chemical reaction, and change in temperature, gets cold or hot when you mix two things together, it'll be a chemical reaction. And you'll be doing this in Beyond Lab Z, which reminds me of something. If you have not yet got your access code for Beyond Lab Z or haven't got it to work, come to my office hour tonight at 5 or after lab tomorrow, and I'll help you do the density lab. Also, if you haven't gotten it, please email me at, send me an email at whitek@cod.edu. And if enough of you, I'm going to go complain to the chairman of the department have her contact a bookstore and say what's going on. So if you haven't gotten your access code for Beyond Lab Z, let me know also tonight or tomorrow after lab. Also, tonight or Wednesday night when I have my office hour 5 to 6:15, if you're considering using my method to reduce test anxiety, stop on by and my office hour. I have a test to find out is the memory you're using good. If you need some practice, I'll help you out. You never have to share the memory that you're using with me, but I have some tests I can find out real quick. All right, let's get into a juicy part of chemistry. Let's talk about chemical equations. I'll never ask on a test, but you should know a chemical equation is a written statement that uses symbols and formulas instead of words to describe changes that occur in a chemical reaction. So chemical equation is a way of showing on paper or on screen a chemical reaction. And I'll never ask you on a test, but there's certain conventions, rules used in writing chemical equations. The correct is important, but people forget about this and try to break these rules. Don't, please. The correct formula for reactants and starting materials are always written on the left side of the equation. The correct formula, actually, I'm turning the switch full on for this, but I'll show you how to learn this right now in a second. The correct formula for the products, substances produced, are always written on the right side of the equation. All right, let's look at a real simple chemical equation. Wrong color. And I'm just using letters of the alphabet. This is A is a chemical, B is a chemical, and C is a chemical. Now, when you see plus, this is where we use the word and. And this chemical equation, A and B, react. Now, on the base of the arrow on the left, the base of the arrow is right here. These are called the reactants. But if you spent decades in the chemical industry like your teacher has, we call these also more likely or not, I'll call them the starting materials. So if you were in academics all your life, you call those reactants. If you come from the chemical industry like I have, we call those starting materials. Now at the head of the arrow, we have C, and we call that the product, or if there's more than one, products. So this is A and B react to make C. Again, A and B are your reactants. The plus sign is really, we use instead of the word and. And if I were to look at a chemical reaction like this one, what are the reactants? What are the products? Well, at the base of the arrow, that's the base, we have our reactants. So the reactants, also known as starting material, are hydrogen, H2, oxygen, O2. The product is water. And that would be that. So I'm going to share the fun. I haven't done it all morning, so I better get to work. I'll make that 2 points. and make it overall 4. And when I put a S in a bracket, that means there could be only one or more than one. Your turn. Have fun. What are the reactants or reactants and the product or products for following reaction? Give you another 6.2 seconds. 6.1, 6.15, 6.175. Time's up. And the reactants are, can everybody read my handwriting or should I print? Let me do a poll. So we'll keep it secret. Even though it says, are you done? Would you like me to, let's do it this way. Can you read my handwriting? Yes. Can you not read handwriting? Cursive? No. Go for it. All right, I know enough. Since enough of you haven't learned cursive, I will stick to printing. And the answer here, the reactants are hydrogen and nitrogen, base of the arrow, are the reactants. And at the head of the arrow are the products. In this case, there's only one, ammonia, NH3. Oh, let's do this again. It was fun. All right. What are the reactants and what are the products for the following reaction? Your turn. And now I am asking, are you done? And it looks like everybody's done, so I better get to work. Remember, base of the arrow, reactants. So the reactants in this chemical reaction are water and sodium. And the products are hydrogen gas, and this chemical is called sodium hydroxide, which we'll talk about later in the semester. And remember, base of the arrow. These are the reactants. Head of the arrow. These are the products. And that's the skill you should have. Hint. Now, I've already shown you this, and I'll never ask this on a test. The reactant and products are separated by an arrow. Oh, and the arrow is always pointing to the products. Plus sign are used to separate different reactants or products. Think of a plus sign as the word and. Now, there's something called the validity check. And switch is totally on now. For a chemical equation, first of all, it must be consistent with experimental facts. If you react two things together and you determine what you make, that should be what you have in your chemical equation. Now, this is very important. You must have the same number of atoms of each kind on both sides of the equation. This is called conservation of mass. In our world, in our universe, you never create or destroy atoms of an element. Therefore, in a reaction, you must have the same number and same type of atoms of each element on each side of the arrow, products, reactants. And we call this having a balanced chemical equation. And now I'm going to be turning the switch up to 20 or dial, even though it only goes up to 10. Now, I'm not going to ask you these things, but I'm going to ask you to know how to use this. For a balanced chemical equation, you have the same number of atoms of each element involved on each side of the equation. And atoms of elements are never gained, lost, or changed into atoms of other elements during a chemical reaction. You don't. This in a chemical reaction. Nuclear reactions, that's a different story. We're not talking about that. Now, let's look at an equation. Now, if we look at H2 plus O2, oxygen, hydrogen reacting to make water, H2O, notice I have two hydrogens here. Oh, look, I have two hydrogens here. I have two oxygens, and for this, I'm going to put a dash so you know I'm not writing the number 20. Two here. Uh-oh, we only have one here. This is not balanced. And we have to make it balanced. And how do we do that? An unbalanced chemical equation is brought into balance by adding coefficients. What's that? That's the number in front of the molecular element in a chemical equation. Right here, when you don't see a number, the number in front called the coefficient, and I'll never ask what a coefficient is on a test, but I will talk about it in class, and that is the number is 1. One hydrogen reacts with one oxygen to make one water molecule. Well, this isn't balanced, and you change the coefficient to just the number of reactant product molecules present. Now, notice I have a note to myself. Remember the torsion balance or teeter-top analogy. Ooh, fancy words today. How many of you have ever seen those chain balances that go up and down? On one side you put weights, the other side you put what you're weighing. And when they're at equal height, it's balanced. And same thing happens, think of, with a chemical reaction. We want to balance the same number of atoms of the same type on each side of the chemical equation, the arrow. Or have you ever been on a teeter-totter? In fact, yesterday when I was out, my neighbor on my back lot, back part of my fence, he has three little kids, and they have in their backyard one of those teeter-totters that goes this way and also goes around, and they were having a lot of fun. He was spinning them around real quick and they loved it. And I can still picture my schoolyard where I grew up. We had just this one that went up and down, a wooden one. And those are fun too. Well, balanced chemical equation, you can't have them. It's got to be like this. So how do you balance a chemical equation? You change the coefficient. Now, the number that's placed to the left of the formula of a substance, and that changes the amount, but not the identity of a substance. Now, this is important. The coefficient is always a whole number, an exact number, never a fraction or a number with a decimal point. Just like I can't ask you, can you go down the hall and get me 1.2 eggs? No, you can't. Or if we were in a classroom, I say, could somebody go outside and find me 1.5 people? You can't. Well, coefficients have to be whole numbers. Now, how do you balance a chemical equation? Well, there's certain things. Write an equation using the correct formulas. You can't change water to something else. Determine if it's balanced, and we have one. Then balance equation one element at a time and check to see if it's balanced. Now, I don't know if I'll get to it today, but don't tell anybody. But Dr. White, I found some really secret ways of helping you balance equations. Guess what? I'm going to share it with you. Let's do a simple one first. Now, as I pointed out earlier, and everybody see the equation oxygen, hydrogen, or hydrogen oxygen makes water on your screen. Thumbs up, people. Do you see it? Thank you. Now, there's 2 oxygen here, but there's only 1 on this side. It should be 2. Well, you can't put a 2 there. Students like to do that. That's hydrogen peroxide. That's another molecule. You can't do that. But what you can do is change the coefficient. If I put a 2 here, 2 times 1, there's now 2 oxygen. There's 2 oxygen here, but 2 times 2, there are 4 hydrogen. Uh-oh, I only have 2 on this side. I want 4. How do I change that? I change the coefficient, the number that goes in front. And here we now have 2 times 2, 4 hydrogen. And I like to do like accounting when you balance your checkbook, which is one of the things I hate to do, but I know it's important. 4 hydrogen, 4 hydrogen, 2 oxygen, 2 oxygen. This is balanced. And what this tells me in this balanced equation, I react 2 molecules of hydrogen. When there's no number there, it's the number 1, with 1 molecule of oxygen to make 2 molecules of water. And that's how you balance a chemical equation. Now, let's look at another one. The first question I would ask you is this balanced? I'll give you 5 seconds. Go. Time's up. And the answer is no, it's not. How do you know? If I look here, I have 2 hydrogens. I only have 1 here. 2 chlorine, 1 chlorine. That's not balanced. Well, if I have 2 hydrogen here, how do I get 2 hydrogen here? You can't put a 2 there. No, students like to do that. That's always wrong. What you need to do is change the coefficient. I want 2 hydrogens. I'll put a 2 there. 2 times 1, 2 hydrogen. But now I have 2 times 1 chlorine, 2 chlorine. If you notice, 2 chlorine on this side. So I have 2 hydrogen, 2 hydrogen, 2 chlorine, 2 chlorine. It's balanced. And that's how you balance the chemical equation. Now, one of the rules, not rules, but things I found out that make your life a lot easier balancing chemical equations. And I will tell you this up front. On test 2, I'll have at least 3, maybe 4 chemical equations that you have to balance, 3 points each. So either 9 or 12 points on test 2. I haven't written it yet, but usually I do put that there. So this is an important skill. And the first, I call them tricks, but they're not tricks. They're just methods that help is leave hydrogen, oxygen last. Do those last. I'm not sure when I came up with that, but it makes your life a lot easier. In other words, you'll be successful. So let's take a look at this molecule. Notice I have 2 nitrogens here, but only 1 there. How do I get 2? I changed the coefficient. So now I have 2 nitrogen, but 2 times 3, 6 hydrogen. And how do I get 6 hydrogen? Because I only have 2. Well, I changed the coefficient. 3 times 2 is 6 hydrogen. And now if I look at this, 6 hydrogen, 6 hydrogen, 2 nitrogen, 2 nitrogen, it's balanced. So I take 3 molecules of hydrogen. Remember, no coefficient. It's the number 1. 1 molecule of nitrogen makes 2 molecules NH3 ammonia. And that's how you balance a chemical equation. And we're doing some practice time. We'll do more tomorrow. Because if I look at the clock, we're just about out of time. Remember, wear your mask. It's dangerous out there in certain parts. Get your vaccination. If you haven't, please do. It's free. COD, I'm sure you got an email telling you clinic coming up soon at COD for free vaccinations. And you can go anywhere else for free. And I'm about to sneeze. But anyways, I will see you tomorrow, 9 o'clock. Don't forget to do your lab, hand it in tomorrow. I have my office hour tonight. If you need help, stop by. I'm always there to help you. And with that, I am out of time. So, gang gesund. Bye.